So the solutions to gravitational fields mutual orbits. A lot of students do struggle with these. They do tend to be quite obviously mathematical. There's these complicated formula which you need to be able to locate and use confidently. And then there's also obviously calculator technique as well. However, like with a lot of physics A level, if you can just take a deep breath and have a process working through slowly and calmly, then the questions aren't actually that difficult, even though at first glance they look difficult. So we're told it's a pair of stars, so we should immediately think, right, it's a mutual orbit. We're told the separation distance, so that's d, so we know d, and we've got the period of 2.5 days. We should be thinking about days in seconds, kilometers into meters, so that should be an automatic thing, thinking about the units. Find the total mass of the system. Now, fortunately, it's told us, i.e. m1 plus m2. So we should be looking at this formula here. This is what we're trying to find. We know big G, we're given the distance, and we're given t as well. So in effect, all we need to do is to rearrange this to make m1 plus m2 the subject, but that can cause confusion. You do need to be confident with your algebra. So we need to get rid of this square root sign. So the first stage is to square both sides. So t becomes t squared, 2 pi becomes 4 pi squared, and then we get rid of the square root just to have everything else on its own. And then we can make m1 plus m2 the subject, so just rearrange, so take that from the bottom to the top, t squared from the top to the bottom, and then it should be a straightforward substitution. But as we said before, we've got to watch those units. So 4 pi squared is straightforward. The d, so 5 million, well, we've got 5 10 to the 9 because it's million kilometers. So it's 10 to the 6 multiplied by 1,000, so that's 10 to the 9, and then cubed, obviously. G, we're given it in the data sheet, and then T, watch out for that. A lot of students would write 2.5, but that's days. We do need the SI units in seconds, so it's multiplied by 24 hours, multiplied by 60 squared. So it's all these little details here, which if you miss out any one of those, obviously you'll get the wrong answer. And then do expect a really big number. Obviously stars can have a range of different big values, but if you're getting something very small, 10 to the 20, 10 to the 25, you should be thinking that sounds a little bit low. Right, that's question one. Okay, question two, same kind of thing, but now we're trying to find the orbital period. And the question's also thrown in something about solar mass. Now, solar mass is not on the EDUCAS specification, and it probably isn't on the other specifications as well. However, examiners do expect you to be able to cope with the information which is not on the specification. So it's told us it's 0.5 solar mass. Okay, 0.25 solar mass. What's the solar mass? It tells us in the question. Okay, so it's just going to be 0.5 multiplied by this, 0.25 multiplied by this. They also tell us about AU. Now, some exam boards talk about astronomical units. It's quite a useful measurement if we're looking at relatively small distances in space. So 1 AU is the average distance between the center of the sun and the center of the Earth. Again, it's not on the EDUCAS specification, and it may not be on other specifications. However, whatever that is, AU, it tells us it down here. So it looks a lot more complicated because they've included things which you may not have studied. But you have to, again, take a deep breath and think, right, what am I trying to find? I'm given the masses. Okay, I can work that out. I'm given distances. Okay, I'm trying to find t. So once again, it's just a substitution, and we don't need to rearrange in this case. It's just make sure we get all the values correctly. So what have we got? We've got d, which is 0.1 multiplied by AU, which we're given here, and then all cubed as per the formula. We've got 2 pi, we've got g, we know what that is, and then we're given m1 plus m2. So you could work out the two values, but it's 0.5 plus 0.25, so that's 0.75 total, multiplied by this value of solar mass, and then we can get the answer in seconds. So normally we would leave that in seconds. If we put that into days and hours, that just gives us maybe more of an idea of how long that is, but obviously we should specify these are Earth days rather than the day on a different planet. So again, mathematically a little bit fiddly, but I think the big challenge here is working with information and ideas, definitions possibly that we haven't necessarily studied, and that can be a little bit off-putting. Right, final one. This is, again, more of an exam question, and it is potentially quite tricky. So we're told the separation of the Earth and Moon. Okay, in this case, they have not told us the mass of the Earth or the Moon. Now, you might be given that in another question, which might make it more difficult, but they've told us that the Earth has got a mass 80 times that of the Moon, but they haven't told us the values. Find the position of the center of the Earth, Moon, and mass system. So they could have phrased this in a very different way. If they'd said, this is the mass of the Moon, M1, for example, this is the mass of the Earth, find R1 or R2, then that would have been a lot easier to identify which formula. But you have to be confident enough to use the information and apply it in the correct way. So we could call this R1 or R2 as long as we get the values of mass the right way around. So let's say we're trying to find R1. So M1 plus M2, we'll come to that in a moment. D, we're told, and we can leave that in kilometers. M2 is going to be the mass of the other thing. So this is where we have to be a little bit algebraic. So let's say M is the mass of the Moon. I think that's right. Yeah, so that's the value we don't know. 80M is the mass of the Earth, so it's 80M plus M, which is 81. So M on top and M on the bottom, and they're going to divide and cancel. So we don't actually need to know the masses. So that's quite a useful thing to be aware of. So it's just 400,000 divided by 81, and we get our value 4940. And we might need to specify where is that. So if M2 was M, that's the mass of the Moon, then R1 is the distance from the Earth to this point. So that's going to be from the center of the Earth. And now we could do this the other way around. I'll just finish this off. The radius of the Earth is 6,400. Oh yeah, good. So that's an extra detail. So actually the center of mass is within the Earth, which is actually, this won't be on the specification, but this is one of the definitions of a planet, so that the barycenter, the center of mass of the mutual orbit, is within the planet itself. Now, if you have a smaller planet-moon system like Pluto with its moon, the barycenter is outside of Pluto, and this is one of the reasons why Pluto was downgraded from a planet, which is a bit of a shame. Yeah, so we could do this the other way around if we want to. So we could find out R2, so that's the distance from the Moon. Now that M1 is going to be the mass of the Earth, so that's 80M. We're still divided by 81M, so the M's cancel, and that's going to be a larger value. So it would make sense that the center of mass is closer to the center of the Earth, which is the value we found over here, and it's going to be much further away from the Moon. So you don't need to do both of these. You could just do one or the other. That's fine, as long as you specify which is which, but they should agree, and it should make sense as well.